بسم الله الرحمن الرحیم. امروز شنبه هست 20 فروردین ماه 1401. اولین جلسه درس زمین آمار به صورت حضوری هست. ما تا کنون بالغ بر 12 جلسه به صورت مجازی داشتیم که عمدتاً تو این 12 جلسه به مباحثی پرداختیم که امکان عرضشون از طریق دکانه وجود داشت. البته جلسات آخری مقداری بار ریاضی داشت، منتها اینا رو بر این گذاشتیم که دوستان ما را از یاد گرفتن محروم نکنن و با طرح سوالاتشون شرایطی رو فراهم بیارن که ما سر ذوق بیایم و شروع بکنیم مطالبی رو که یا نگفتیم یا اگر گفتیم یه جوری گفتیم که برای شما سوال ایجاد شده به یه زبان دیگری بیان بکنیم که انشاءالله حق مطلب ادا بشه. پس استدعا و خواهش عاجزانه بنده این است که در طول کلاس هر موقع ابهامی، ایرادی، اشکالی وجود داشت بزرگواری کنید، سوال کنید. سوال کردنم حق مسلم شما هست و با پرسیدن شرایطی رو فراهم میکنید که حق مطلب ادا بشه. و از یک سو هم بنده هم حداقلش این هست که متوجه میشم که این مطلبی که گفتم باید در بیانش تجدید نظر کنم که بهتر ادا بشه. همونطور که خدمتتون یادداشتی رو از طریق ایمیل ارسال کردم، سعی میکنم یه خلاصه‌ای از مطالب این 12 جلسه رو خدمت عزیزان مطرح کنم و بعد میریم سراغ آشنایی بیشتر با توابع تصادفی random functions که عمدتاً موضوع این کورس هست. قبل از اینکه شروع کنم این خلاصه رو عرضه کنم، اگر کسی بارش فکری بذاریم سوالی داره که فکر میکنه طرحش میتونه استر رو آماده کنه برای ورود به درس، خوشحال میشیم. بگیم ما مثلا این مطلب از 12 جلسه رو متوجه نشدیم. کسی سوالی موردی؟ البته نپرسیدن باز از دو حال خارج نیست، یا اینکه مطلب خیلی روون بوده یا اینکه خیلی سخت بود. اگر روون بوده سوال تولید نشده، اگر خیلی هم سخت بوده که همش دیگه سخت بود، نمیتونیم کجاش دست بزنیم. در هر دو حالتش میمون مبارک. به طور کلی perhaps you know that we have to speak in English in this class as opposed to advanced engineering mathematics where we taught in Persian. It really doesn't matter whether you are in groundwater hydrology or water resources engineering or whatever discipline you might imagine. In any discipline, if you are given a state variable, dependent variable, and you would like to characterize this state variable or dependent variable or field variable on your own, this field variable should have 4 arguments. Therefore, imagine that your state variable under consideration is y. And then you would like to characterize this y. This y could be precipitation, this y could be piezometric head, this y could be hydraulic conductivity, You can go on and on and on and write down a variety of regionalized variables where the argument that I'm going to talk about is very applicable to them. The very first argument that I should put here is space. The temperature here is very different from the temperature outside. Variation of temperature from inside to outside. And this space, of course, can be replaced with X, Y, Z in 3D, or X and Y in 2D, or X in 1D. The next argument that you have to put here in order to claim that you are planning to characterize Y is time. Again, if you put a thermometer here and monitor the temperature at this point would change from one instance to another. And then the next argument that I need to put here is inherent randomness. We try to interpret inherent randomness from two viewpoints. The very first viewpoint to justify inherent randomness has something to do with measurement. We have to monitor the state variable and their consideration. And the very first sentence that we offer in a course on numerical analysis is this: every measurement in every branch of science is corrupted by noise. You cannot have a typical measurement free from error. It really doesn't matter whether you are here or in LBL Berkeley. Every measurement in every branch of science is corrupted by noise. It makes no sense to talk about certainty, but it makes a lot of sense to talk about uncertainty. This is the first justification for considering your state variable to be equipped with inherent randomness. The second justification for taking this inherent randomness into account has something to do with prediction. If you put a thermometer here and then you are faced with a simple question: what would be the temperature at 4 o'clock today? You cannot say that the temperature at 4 o'clock today is going to be this for sure. But you can say with some plus and minus that the temperature is going to be, say, 15 degrees centigrade. And the final argument that you need to put here has something to do with directional variability. It's quite interesting, or perhaps better to say, one obstacle for efficient learning in various disciplines has something to do with using different terminologies. And this is very unfortunate, by the way. Why? Let's talk about the space or spatial variation. If you are in groundwater hydrology, where some of you are coming from groundwater hydrology, then you will denote a spatial variation by homogeneous versus heterogeneous. By homogeneous, we mean the partial derivative of y with respect to space is 0. By heterogeneous, we mean the partial derivative of y with respect to space is not 0. If you are coming from surface water hydrology, then the terminology associated with the spatial variation will be lumped versus distributed. For a lumped system, such as unit hydrograph, the spatial variation of the attribute under consideration with respect to space is 0. But when it comes to distributed system, the partial derivative of the attribute under consideration with respect to space is not 0. And then if you are coming from stochastic hydrology, then neither homogeneous versus heterogeneous nor lumped versus distributed would be applicable. Out there, we will use space independent versus space correlated. But it's a question of different naming for the same concept. When it comes to time, some people will refer to time as steady versus unsteady. Some other refer to time as static versus dynamic. And some people prefer to denote the unsteadiness by transient instead of unsteady. When it comes to inherent randomness, you have to differentiate between two concepts: deterministic approach, a stochastic approach. If you have a system where there is no inherent randomness associated with any state variable or parameter or output variable, then you would say your system is deterministic. Similar input will give rise to the same output every time that you will introduce that input into your system. However, if your system is stochastic, by the way, by stochastic I mean partially deterministic, partially stochastic, as opposed to probabilistic, where your system is purely random. Therefore, probabilistic will lie between deterministic and stochastic. And it's a spectrum. At one side of the spectrum, you have total ignorance, jahl mutlaq, and on the other side of the spectrum, you have truth. As you move from total ignorance, absolute ignorance, toward total determinism, truth, your knowledge will be enhanced. But you cannot get rid of uncertainty. That is the fact. I shared a seminar from International Association for Hydrologic Research with you, and I raised a question in assignment number 2 in order to create a constant for you to watch the webinar, and the webinar is totally devoted to uncertainty. And you have a chance to look at the number of papers cited in that seminar or webinar, and I shared those papers with you, and I hope you enjoy reading those papers for possible digging into the uncertainty issues. Directional variability, fortunately, has the same name in any discipline. Isotropy versus anisotropy. If your system under consideration is isotropy, then that means the attribute under consideration would not change with direction. However, if your system is anisotropic, then that means the attribute under consideration would change with direction. We can replace those names by its argument. X, Y, Z, T, omega, theta. It might be interesting for you from now on if you start to read a paper. Please pay attention. If you start to read a paper, the very first question that should hit your mind is to answer this question. What are the arguments considered in that paper? Make a decision whether the paper is deterministic or stochastic by touching on inherent randomness. Make a decision on directional variability, whether the system under consideration is isotropic or anisotropic. Decide on your system regarding steady versus unsteadiness. And then when it comes to spatial variation, make a decision on lumped versus distributed first, and then as soon as you realize that your system under consideration is distributed, then make a decision on 1D, 2D, or 3D problem. What would be the benefit of this initial understanding? Perhaps you might read a paper for different objective. One key objective in your reading the paper is to hunt a topic for further research. از خواندن یک مقاله هدفتون این هست که یک سوال فاقد پاسخ شکار کنید و بعد با پاسخ به این در واقع با شکار این سوال فاقد پاسخ یه بستری رو برای تحقیق فراهم بکنید. One way to create or delineate an unanswered question is to make this decision. If the paper considered isotropic situation to write the paper, then what if you include anisotropy? If the paper assume that your system under consideration is steady, then what would be the cost associated with assuming that your system is not steady, transient? If the system is lump, then your task is to see if you can convert it to distributed to answer a few questions. I'm going to share a link with you perhaps toward the end of the week, because I asked the student to prepare some bullet type comments for her recent Master of Science defense. And I'm quite sure by looking at that defense you will enjoy following what she did. The title of her thesis was Investigating the Spatial and Temporal Variability in Rainfall on Catchment Response. I imagine that you took part in her defense because I saw your name, Mrs. Hadith Ziyahi. I uploaded the file in Apparat, and I'm quite sure based on what I said today, you will closely follow what she did, and it is very important for you and me and anybody else to have a clear question for research. It's very important. From time to time, I took part in a webinar. I took part in a defense session. And to be honest with you, I was not able to delineate the unanswered question that the investigator is planning to address. It's very important for you to be equipped with a typical research method, to be able to address an unanswered question. And as I said, from time to time in this course or some other course, 50% of your research activities concerned with delineating an unanswered question. And your bottleneck, I would say, at PhD level, is to delineate an unanswered question, which deserve further research. این تکه رو بخاطر اهمیتش به فارسی بگم. یکی از چالش های شما، حالا آقای مهندس ظاهری یکم جلوتر میتونه یک کامنتی رو این بده. یکی از چالش های شما بعد از دوره آموزشی، دوره پژوهشیه که چی چالش چی دوره پژوهشی؟ شکار سوال فاقد پاسخ. چرا؟ چون هر بابا مرده ای رفته یک کاری کرده، پخش شده توی جورنال مختلف و اگر روی دیتابیس های متعارفی مثل ساینس سایتیشن ایندکس یا اسکوپوس یا انجینیرینگ ویلیج، حالا انشاءالله یه فرصتی هم شد، چون خرده دیگه حالا توی این 2 ساله تنها چیزی که دستگیر ما شده آموزش مجازیه. یه توری توی دانشگاه واترلو براتون میذاریم، البته توی این مجموعه‌ای که خدمتتون ارسال کردیم آخرین جلسه اختصاص دادیم به معرفی وب آف ساینس که همون ISI شما میشه یاد گرفتید. ISI وب آف ساینس، دیتابیس وب آف ساینس بس شدیم به دانشگاه واترلو و شروع کردیم برای 47 نفری که تو کلاس حضور داشتن از اساتید عرضه کرد. حالا یه فرصتی شد چون روز به روزم باید تفاوتی نسبت به روز داشته باشیم، یه جلسه مجازی هم باز خارج از وقت میذاریم که این رو برای این که شما آشنا بشید با چیز. البته الحمدلله الان دیتابیس دیگری هم هست که دسترسی بدون آیدی پسورد رو فراهم می‌کنه. What I said has something to do with comparing and contrasting deterministic or continuum mechanics or Newtonian mechanics with statistical mechanics in the PowerPoint before the Nowruz holiday. The next topic that we consider has something to do with how to structure various variation into a single flowchart. For the time being, in that PowerPoint, I did not consider directional variability. I only touched on spatial, temporal, inherent randomness. If I want to have a very brief summary of what I did with regard to those flowchart for deterministic versus stochastic, lump versus distributed, and then steady versus unsteady, I have 4 possibilities under the umbrella of deterministic approach, 4 possibilities under the umbrella of a stochastic approach. Therefore, if I put deterministic here, and then stochastic here, four possibilities under this title, four possibilities under this title. If I put y, and it's very important for you and me to differentiate between y lowercase letter and y uppercase letter. Because I am here, I have to write y in lowercase letter. If I did not assign any argument to y, this means my system is numb and steady. No argument. If I assign t but not s, that means my system is unsteady but numb. If I assign s but not t, then that means my system is distributed but steady. And finally, if I put s and t simultaneously, then that means my system is deterministic because y is lowercase letter, distributed because s is included, and transient because t is also included. I try to provide a few examples from the different disciplines for each one. If you are in hydraulic, then the best example to represent y only is uniform flow, where the depth of water and the velocity neither change with time nor space. If you are in groundwater hydrology or surface water hydrology, the best example for this case is to have a regression-based modeling. Try to correlate 10-year return period flood with physiographic characteristics of your watershed. For this case, a typical example in hydrology would be unit hydrograph, where you do have the temporal variation but no spatial variation. And of course, there is no inherent randomness for none of them because your system is deterministic. That is a typical example in surface water hydrology, unit hydrograph. A typical example from hydraulics is going to be rigid column analogy, design of surge tank. When it comes to this case, a typical example from hydraulics would be hydraulic jump or spatial well flow or gradual well flow. And a typical example from groundwater hydrology would be Laplace equation or Poisson equation, where there is no temporal variation, but the state variable under consideration will change with respect to space. And when you are here, if you are coming from groundwater hydrology, then the typical example is going to be Tate's equation, where the attribute under consideration would change with respect to space and time. If you are in hydraulics, then central equation is going to be a typical example. There's another roadmap associated with these four possibilities. And it's quite important to be familiar with these possibilities. And I would argue why you need to be exposed to these aspects as well. The governing equation for each case. The governing equation for this case is algebraic equation. The governing equation for this case is ordinary differential equation. Of course, if your system is continuous. If your system is discrete, then it's going to be algebraic. If you are here, it doesn't matter whether your S is 1D, 2D, or 3D. If S is 1D, then your governing equation is going to be ODE. If your system under consideration is 2D, then the governing equation is going to be partial differential equation. Finally, if you are here, the governing equation is always partial differential equation. And Mrs. Veda's Rajabzadeh is very familiar with these governing equations when it comes to a course on advanced engineering mathematics 2. How could it be possible to solve these governing equations analytically? Another aspect that you might enjoy to be exposed to is this. If you want to solve this system, of course here the attribute under consideration, the unknown, is going to be under the total differential sign. Here the unknown is either going to be under the total differential sign or partial differential sign, depending upon the number of spatial dimensions. And if you are here, the unknown is going to be under the partial differential sign. Question, and it's very important to know the answer to this question. What about integral equation? There is no trace of integral equation here. But we said we have 5 types of equation. Algebraic equation, ODE, PDE, IE, and then mixed equation. This central equation, if you collapse it to kinematic wave equation, then it's going to be algebra differential, partial differential equation, which means it is mixed. Any comment, any argument on what do we mean by integral equation? Where did we learn something about integral equation? Where the unknown is under the integral sign? We do have a course on finite element analysis in this semester, where Mr. Mir Ahmadi took that course. And in that course, we argue that any problem in any branch of science has 2 formulations. Differential formulation, integral formulation. You can convert differential formulation into integral formulation. And then the justification for moving from differential formulation to integral formulation is huge. I shared a document with a student where I touched on advantages of integral formulation by 8 items, 8 bullets. The advantages of the integral formulation compared to differential formulation. What about this? When you are here, under the stochastic umbrella. If you are here, then you have to change this y lowercase letter to y uppercase letter. And then the argument will give you the four possibilities. If you consider only the spatial value, the inherent randomness for y, that will give you a discipline so-called frequency analysis that we try to cover in our PowerPoint presentation. Frequency analysis. We have two types of problem here. And in those problems, if I want to summarize them, in problem type 1, you are given n years of instantaneous maximum flood for a typical section at a typical river. Q1 is the instantaneous maximum flood for year 1. Q2 is the instantaneous maximum flood for year 2, and so on. And then you are given the return period. You are asked to compute the magnitude of flood corresponding to this return period. In problem type 2, again you are given instantaneous maximum flood at a particular section in a typical river. Are you changing the camera when I change my position? Okay? Instead of knowing the return period, we are given the magnitude of flood. And then we are asked to compute the return period associated with this Q. We denote this by QD. These are two types of problem in frequency analysis. In a course in engineering hydrology at Bachelor of Science, we cover these two types of problems. And I'm quite sure that you, in a course in hydrology in your Bachelor of Science, will also touch on this type of problem. And that is why your course in engineering hydrology should have a prerequisite so-called probability and statistics. پیش نیاز درس هیدرولوژیتون آمار هست. چرا؟ خاطر آنالیز فراوان. The next three items that I should put here, everyone should have omega as one argument. Why? Because they are under the umbrella stochastic, of stochastic. Now, the second, I should put T omega. Which means that my system is time correlated and it is stochastic. If you put a thermometer here, please pay attention. If you put a thermometer here, then the temperature at an instant in time cannot be considered to be independent from the temperature in the next hour. What does that mean? If the temperature right now is 15 degrees centigrade, then the temperature 1 hour later cannot be 25 degrees centigrade. Why? That type of abrupt change, sudden change, cannot occur. It will gradually change from one instant to another. Therefore, it is highly correlated in time. We have a discipline so-called time series analysis. Analysis سری‌های زمانی, where Dr. Somani is an expert in time series analysis. I recall he offered a course on time series analysis, and Chatfield is his reference. The next possibility is to have your attribute under consideration to be a function of space and inherent randomness. Which means that your attribute under consideration is space correlated, and you should consider inherent randomness in your computation. And also spatial series, that is geostatistics, is here. And finally, when it comes to spatial-temporal geostatistics, you have spatial variation, temporal variation, inherent randomness. Please compare this to this. The only argument that you have here compared to here is the inherent randomness. How about the governing equation? It's very important to be able to delineate the governing equation here and try to see what is the difference between this column and this column as compared to governing equation. The governing equation for this case is algebraic equation, probability distribution function. When it comes to this, it depends upon whether you would like to consider your system to be continuous or discrete. If your system is continuous, then the governing equation is going to be a stochastic ordinary differential equation. Here your governing equation is ordinary differential equation. All you need to do to characterize the governing equation out there is to put stochastic in front of ODE. A stochastic ordinary differential equation. Here, just like what you had here, it depends on the number of spatial dimension. If your number of spatial dimension is 1, then the governing equation is going to be stochastic ODE. If the number of dimension is more than 1, then you are going to have a stochastic partial differential equation. And then when you are here, your Gordon equation is always stochastic partial differential equation. Whether you are here or you are here, your task is, please pay attention to this point. Mrs. Rajabzadi is very familiar with this idea. Whether you are here or you are here and you are asked to solve a typical problem for this part or this part or this part, your overall task is to convert this ODE or PDE or PDE into algebraic equation. مثل این نسخه هست این صحبت. یعنی اگر چنانچه شما بخواید از بیرون به دیسیپلین های مختلف نگاه کنی، به برانچ‌های مختلف ساینس نگاه کنی، حالا چه دیدگاه انالیتیکال باشه چه نیومریکال، it really doesn't matter. واقعا مهم نیست که دیدگاهتون انالیتیکال یا نیومریکال باشه. یکی از اینها رو بخواید حل بکنید، وظیفتون تسکتون این است که تبدیلش بکنید به الجبر اکویشن. یه لحظه برید فکر کنید ببینید همین هست یا نیست. این مطالب ما گفته بودیم. حالا تفاوت بین کلاس حضوری و مجازی چجوری توجیه میشه؟ خواهی من نیست
بهتر چه میفته؟
بیشتر. When you are here, you have 4 possibilities. Just like when you are here. What are those 4 possibilities? If you neither freeze the spatial variation nor inherent randomness, then you are going to have a random function. If you freeze the spatial coordinate but relax the inherent randomness, then you are going to have a random variable. Particular point in space, you have a various realization. It's going to be a random variable. If you freeze the index corresponding to inherent randomness, but leave a space to change over the spatial domain, then you have an ordinary function. Please pay attention. As soon as you have an ordinary function, you have to change y uppercase letter to y lowercase letter. Ordinary function. The attribute under consideration in changing over the spatial domain adds a particular realization. And then the final possibility is to freeze both spatial variation and inherent randomness. A single number. You have to write the full name because these are very personal. Sooner or later you will forget what do I mean by SN, single number. As I said, these 4 possibilities is very applicable here. If you neither freeze the temporal variation nor the inherent randomness, then you are going to have a random function. If you freeze the temporal variation but relax the index corresponding to inherent randomness, then you are going to have a random variable. If you freeze the inherent randomness but consider t to change from one instance to another, then you have an ordinary function changing with time. Then if you freeze both temporal variation and inherent randomness, then you are going to have a single number. The number of possibilities here is more because you have 3 arguments. I did purchase a book for Khwarazmi library. Right now the book is in my office. And the title of that book is Spatial Temporal Geostatistics, written by George Christos. Spatial Temporal Geostatistics, where you will consider the spatial and temporal variation simultaneously. Of course, inherent randomness is in place as well. The general problem statement, just like what I did here for frequency analysis, is very applicable here, here, and here as well. Please pay attention that from now on, as I said on those autoconic session, when you are here, instead of writing y as a function of t and omega, you will simply write y as the function of t. And this y uppercase letter takes care of omega. Okay? This uppercase letter will take care of omega. Compare it to y lowercase letter as a function of t here. From now on, I will denote y as a function of s. But I really mean that the second argument is inherent randomness. Because I write this y in uppercase capital letter, then that means omega is in place. If I write y in lowercase letter, then that means this way of writing the attribute under consideration is very applicable here. Which means that here, if I write y as a function of s, then that means I'm talking about a random function. If I write y as a function of si, then that means I'm talking about a random variable. The nature of randomness concerned with writing this in capital letter. And then if I write y as a function of s, that means I'm talking about an ordinary function. Of course, I have to write omega here because omega should be here but not here. Here omega is freeze. Do you know what I'm saying? I have to write just like others. Omega are not freeze in these two, but omega is freeze in these two as well. Because omega should be in place, but when I am here, I will eliminate omega. And then if I am here, I have to write y as a function of s. It's very important to differentiate, make a distinction between these, and assuming that omega is always in place. Now, problem statement. We have two types of problem in time series analysis or in spatial series analysis. The good news is this. Here, instead of talking about stochastic ODE or stochastic PDE, we will consider our system to be discrete. And by discrete, we mean we are not going to solve a stochastic partial differential equation. Instead of having a stochastic partial differential equation which has something to do with finite element, here we will assume that instead of having the governing equation, we are given a single partial realization of a random function. Why? If you want to interpret this y as a function of this I, you have to be here. Which one is it? The second. And what is that? Random variable. You have a random variable at spatial location is 1, another random variable at spatial location is 2, another random variable at spatial location is 3, and so on. Aggregation of these random variables will give you the random function. Another way to look at these four scenarios and these four scenarios is this. Here you have a scalar quantity. Not a function quantity. When it comes to here, here, and here, you have a function quantity. Because it will change with respect to space or time for both of them. And your scalar quantity here is a crisp number. What does that mean? You have to specify the magnitude only. By the way, if it happened that you are talking about hydraulics and then you would like to see what will happen to velocity, no doubt, velocity should be put here. But velocity is a vector, but there is no argument. And this uppercase letter, if I want to be more specific, I have to write it be lowercase letter to be consistent with uppercase versus lowercase letter. This V here is velocity. That velocity is not a scalar quantity. Velocity is a vector quantity. And since there is no argument associated with it, with this velocity, then you will assume that your velocity is lump. No spatial variation, no temporal variation. Uniform flow is equipped with this feature, where the velocity would not change with respect to time and space. When you are here, better to say, when you are here you are going to have a purely random variable. What would be the implication؟ پیامد ناشی از داشتن یک متغیر تصادفی اینجا چیه؟ If you want to define a problem here, your attribute under consideration should be purely random. What does that mean? That means your Q1 up to Qn has to be a purely random process. No temporal, no spatial correlation between Q1 and Q2. Another way of defining this is to say, here your Q1 up to Qn are n realization of a single random variable. N realization of a single random variable. But when you are here, you cannot say n realization of a single random variable. You have to say you have n random variables where their aggregation will give rise to a random function. That is another way on how to move from statistics to geostatistics. Given a single partial realization of a random function, then you are asked to estimate the attribute under consideration at the point which is not sum.
مورد قبلی که توضیح میدادیم که صحبت از این بود که ما زمانی که میگیم استوکاستیک بحث میکنیم و میگیم یک کیو داریم تو یک دو، این یک دوش هم باید مثلا یک رندوم باشه و ما نمیتونیم مشخص بکنیم. اصطلاح عملیش الان چی میشه؟ مثلا به فرض ما داریم روی جریان صحبت میکنیم، این یک دو اینا مستقل از زمان، با حالت اولی باید مستقل از زمان، مستقل از مکان باشه. مثلا میگم Q1 به چی اطلاق میشه و بعد Q10 به چی اطلاق میشه.
اگر if you have a river like this and at a particular cross section you have a hydrometric station, you may be familiar with how to monitor the stream flow at a particular hydrometric station. For each river at every water year, Salabi, we have 365 numbers for each year. If you single out the maximum value out of these 365 number at year, say 1370, then that will give you Q. The next year, 371. You have 365 numbers. Single out the maximum number. That will give you Q2. The next year, Q3. The next year, Q4, up to the final year where it is right now. Therefore, this 1, 2, 3, 4 has something to do with water year, Salabi. Instead of writing 1, you could write Q.
یه سوال، الان مثلا همین داخل مورد خاص شما فرمودین که هر کدوم از اینا مربوط به یک سال آبی هستن. خب فرقش با اون حالت دومی که وای ما متغیری از T و اومگا هستی.
Very good question. That is where a scale will come into consideration. A very good question to raise here. If you start to increase the time span, if you start to increase the spatial extent, then the chance to get a purely random process would increase. Look at the way that you will collect these data. The instantaneous maximum flood at year 100, 370 is independent from the corresponding maximum flood in another year because it will cover 4 seasons. However, when you are here and you would like to, let me write the corresponding 4 scenario here. If you neither freeze the time nor inherent randomness, then you have a random function. If you freeze time but not inherent randomness, then you are going to have a random variable. random variable at now I should write, because here I have a 1D plot. This is y at t1, this is y at t2, and this is y at t3, and so on. I have a random variable at this point, I have a random variable at this point, I have a random variable at this point. The very first thing that I need to decide the nature of the attribute. The nature of the attribute, by the way, Q1, Q2, Q3, here, again, you could have a line here. This is year number 1, this is year number 2, this is year number 3. The question that Mr. Zohir is raising is this. Mr. Abedini, here you would say your attribute under consideration is purely random, but what should I say here? And what would be the attribute to put here? Should I put the same item here or another? If you consider daily stream flow, then your daily stream flow cannot be considered to be independent. Why? The flow in the river today is 100 cubic meters per second. Tomorrow it cannot be 0. You are familiar with base flow. Your base flow is very smooth, decreasing. It cannot suddenly change to 0. Therefore, if you are in time series analysis, you have to take your attribute in such a way that that spatial or temporal correlation can be detected. But if you increase the temporal variation, the temporal extent, then the chance to get a purely random process will increase. Here, the interval is 1 year. Here, the interval is 1 day. Can you see? If you are talking about daily stream flow, then you cannot assume that your process under consideration is purely random. But if you consider yearly instantaneous maximum flow, then you can assume that your attribute under consideration is a purely random process.
میشه این شکلی تصور کرد که صحبت از مقیاس زمانیه.
It is very applicable to a spatial scale as well. If you look at that paper that I shared with you, Scale Issues in Hydrological Modeling, a review, everything that the author said about temporal scale is very applicable to a spatial scale as well. And it's a very hot topic, by the way, scale issues. Can you see the difference between physical session and virtual session? I am face to face with you. I can imagine where you will follow me and where you are very surrounding. What is he saying? And then the question is, this Q1, Q2 correspond to this here, not here. And then you are asked to estimate attribute under consideration at the point which is not sampled. This is a typical question in univariate geostatistics. Estimated value. Please pay attention. In real life, please pay attention. In real life, we do not have a random variable at each spatial location. We have a single number. But because our framework is stochastic, we pretend that we have a random variable at each spatial location to be able to go for estimation. If I want to state my problem in Thyssen polygon, because Thyssen polygon is a deterministic approach, what I need to do is only to change this y uppercase letter to y lowercase letter, because the Thyssen polygon approach is deterministic, not stochastic. Out there, your framework is not stochastic. Your framework is deterministic. That is univariate geostatistics. By univariate, I mean I try to estimate the same attribute as the one that I'm given. When it comes to multivariate geostatistics, given y sub I S of j I can go which means that I have how many random functions? N random functions. y1, y2, y3, y4, up to yn. And then the spatial index corresponding to each random function would change by tradition. We will assume that y1 is our primary variable, y2, y3, y4 and so on are our secondary variables. And then the question is, estimate primary variable at the point which is not some. This is multivariate geostatistics. Look at your discipline, groundwater hydrology. Piezometric head is highly correlated to hydraulic conductivity. Therefore, it makes a lot of sense to enhance your cross-validation statistics by taking into account hydraulic conductivity as well to estimate piezometric head. Which means out there, in that example, you have two random functions. Piezometric head is your primary variable, hydraulic conductivity is your secondary variable. And you would like to estimate piezometric head using both piezometric head and hydraulic conductivity. The reason that I argue that here your system is discrete concerned with this formula here. When you are in univariate geostatistics, the estimated value of y at the point which is not sample can be written as a linear combination of observation. Estimated value of y at the point which is not sampled can be written as a linear combination of observation. This is linear geostatistics. when you are here, estimated value of primary variable at the point which is not sampled. If you look at the session that I shared with you in Apparat, out there I used 2 index for spatial variation. I consider 1, assume that this one is the same as this, and this 0 implies that I have no measurement at a spatial location S10. And then I have to consider both primary variable and secondary variable to enhance the cross-validation statistics. I from 1 to n, y1 s, I have to write lambda first, lambda 1i times y. Of course, this lambda 1i will be a function of S10, just like what I have here, times y1 S1i. These S1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and so on are the places where I monitor the primary value. Plus j from 1 to m, lambda 2j, which is a function of S10, times y2 Sj S2j. Please pay attention. In my problem statement, I assume that I have n random function. But when it comes to estimation, experience shows that more than 2 random function would not work, would not enhance the cross-validation statistics. Only 2 random function in multivariate statistics. I have never ever seen a paper assuming that we have 3 random functions. Only 2. As an example, precipitation. Precipitation is highly correlated with elevation. Therefore, precipitation will become your primary variable, elevation will become your secondary variable. For those of you who work on contaminant transport, you could talk about turbidity. Turbidity as primary variable is highly correlated with suspended solid. Therefore, if you want to enhance the cross-validation statistics, you could include suspended solid as your secondary variable to enhance the goodness of fit criteria, as opposed to taking turbidity alone for your estimation.
So, sorry, مثلا تندیس استاپ میشه 10 یا 1 من نمیدونم متوجه نمیشم.
This one corresponds to one here, implying that you're talking about primary variable. These 2 here implies that you're talking about secondary variable. And you have some other issues that I will consider them when I started to teach multivariate geostatistics. You could have a scenario like precipitation and elevation where they are collocated. What do I mean by collocated? at the same point that you monitor precipitation, at the same point you have elevation. But it may happen in nature that the place that you monitor your primary variable is very different from your secondary variable. That is why I differentiate them by writing one I, 2J. This I would change from 1 to n, which means that you have 1, 1, 1, 2, 1, 3, 1, 4, up to 1n. When it comes to this j would change from 1 to n. And then you have 2, 1, 2, 2, 2, 3, 2, 4, up to 2n. And the index implies that this monitoring places for primary variable and secondary variable are very different. Of course, it seems that I have 10 here, but this 10 is not really 10. But this one corresponds to this, and this 0 corresponds to this 0 here. No doubt, the coefficient corresponding to your secondary variable will be a function of S10. Please pay attention. I did not say S10. I said S10. 1 corresponds to primary, 0 corresponds to an estimated value. Now, we are left with a few minutes. This question is not from Mr. Mir Ahmadi, but from everyone. Your next class is going to start when? کلاس بعدی که شروع میشه؟
10:30
شروع میشه. شما وضعیتتون چجوریه؟ نداره کلاسمون کجا تشکیل میشه شما؟
فقط من
فقط خانم رجب زاده دارم.
دکتر بیدختی هنوز اطلاع ندادن که آقا کجای تشکیل، چون فقط من
ایشون نداره کلاس؟
نه من ندارم. ما ریاضیات فقط خانم رجب زاده دارم.
ریاضیات کی دارید شما؟
فردا صبح
صبح بود؟
هفته‌نی دانشگاه مکانیک استاد داریم. حضوری.
چند نفری؟
الان شده 5 نفر. 6 نفر تقریبا شده. 2-3 نفر هم از کلاس شما آمدن.
Perhaps it makes a lot of sense to touch on another topic in this brief introduction, or perhaps summary of what we did in previous lectures, touching on 2 measures when it comes to estimation. In time series analysis as well as spatial series analysis, we have 2 measures of either similarity or variability. Measure of similarity. By measure of similarity, we mean the degree to which your random variables distributed in time or space are similar. We have to measure to quantify similarity. This first measure is covariance function. By covariance function, I mean covariation between 2 random variables. In statistics, not geostatistics, but this definition is very similar with one minor change. Out there, we will argue that covariance between random variable x and y. Can be written as expected value of x minus mu of x times y minus mu of y. This is how to define covariance function in statistics. You can simplify this to a more usable equation by writing this as expected value of xy minus expected value of x times expected value of y. And that is part of your job, to see how you can convert this to this. And I would suggest to do this to see what's going on by converting this to this. This mu is the expected value of x, which means that you can replace this with mu x and this with mu y.
دیگه چند بارم تکرار شده بستیم راجع به تابع امید میشه چون حقیقت شما تا برخوردی نداشتیم نمیتونیم تابع امید اصلا چیه؟
امید ریاضی؟
بله.
چی بگم قبل امید ریاضی؟
چی هست؟ چطور؟ یعنی معادله خاصی داره؟
نه the expected value
چی هست؟
the expected value of x depending upon the nature of this argument here can be defined as
احتمال
if x is a discrete random variable like what? The number of rainfall event within a year is a random variable. Why it is a random variable, Mrs. Zare? No. I argue that the number of rainfall event within a year is a random variable, and I am asking why the number of rainfall event within a year is a random variable. علت این که تعداد حوادث بارندگی در یک سال یک متغیر تصادفی چیه؟ حالا حداقل حالا هر دو موردش تفسیر میکنم، هر دو مورد تصادفی تفسیر میکنم. آیا سال آبی تو هر سالی از 1 مهر شروع میشه تا 31 شهریور سال بعد؟ الان سال آبی چیز تموم نشده چون باید 31 شهریور بیاد تا تموم بشه. یه تعداد ایونت اتفاق افتاده، میتونید بشماریدش. حالا اینکه شمارش ایونت ها رو با چه ملاک انجام میدی سوال دارم روش، چون کار کردیم روی میتونید بشمارید تعداد ایونت ها رو، ولی با قاطعیت نمیتونید بگید تا 31 شهریور 1401 چند تا ایونت دیگه خواهید داشت. به همین خاطر میگید تعداد ایونت ها چیه؟ تصادفی. یه تفسیر دیگر هم داشتیم، تفسیر دومی هم برای ماهیت تصادفی داشتیم، مثلا اندازه‌گیری بود. میگفتیم چون ما باید اندازه‌گیری کنیم. حالا خانم رجب‌زاده میگیم ما که دیگه نمیخواد اندازه‌گیری کنیم، بارم میگیم میاد یه شروع داره، یه اتمام داره، میگیمش 1 بشمار، 2 بشمار، ساعت. اگر چنانچه یه وقته بینش بود بین بارندگی دوباره یه بارندگی شروع شد، این یکی بدونی به 2 تا بگی
مثلا براتون یه روز
به طور کلی اگه وقت هم بینش باشه و وقفا بینش باشه، مثلا حالا شما در مقیاس روزانه میخوای شمارش انجام بدی، من میگم در مقیاس ایونت نه روزانه. سرگردان میمونه که این فاصله که بینش افتاده توی یه ایستگاه فاصله بینشه، نه خونده شده، توی یه ایستگاه خوانده شده و شما سرگردان میشی. این اسمش بذار خطای اندازه‌گیری. ولی کلاً بحث تصادفی بودن تعداد بارندگی ها میتونه ناشی از این باشه که به طور قطع نمیتونه تا آخر 31 شهریور توی چند تا مورد استفاده بشه. That is a discrete number. That is a discrete variable. گروه خونی is another typical example of discrete random variable. The number of automobiles reaching a cross-section within a particular time horizon will be considered a random variable. Why is it random? The number of automobiles reaching a cross-section چهارراه در طول روز. You cannot say for sure tomorrow how many automobiles reach the cross-section.
تصادفایی که یه سری چهارراه اندازه نمیشه.
چی؟
تعداد تصادفات چیزایی گفتیم؟
نه، گفتم تعداد اتومبیل هایی که وارد یه چهارراه میشن. حالا تصادف هم یه مثال دیگه. تصادف هم که در داخل یه شهر اتفاق میفته دیسکریت. However, if I give another example telling you the time spent by you to reach the school from your home, can I assume that your no, it is continuous. You cannot assume that the time spent to reach school is discrete random variable because it has to be with significant digit. با اعشار همراه هست زمانش. In fact, the implication for taking the time horizon you will spend to reach school to a purely random process has something to do with structuring your daily program to reach school. The expected value of this random variable should be considered in your plan to reach school. The expected value. What does that mean? You have to collect numbers, the time horizon that you will reach the school for a particular semester, and then the next semester use those numbers to find the expected value, the mean. And then based on that mean you will organize your daily activities to reach the school. If your random variable is discrete, then all you need to do is to use this equation to compute the mean. If your random variable is continuous, just like the time horizon you will spend to reach the school, then that's going to be the expected value of x. When your random variable is continuous, you have to use this equation to find the expected value of x. When your random variable is discrete, you have to use this equation to obtain the expected value of it. That is the definition of expected value. Can you tell me what can I do for this expected value of xy? If I want to write something like what I have here, what should I write for expected value of xy in terms of definition? If I want to I will leave this volume to fill it out, and I will write the continuous version of this. If it happens that x is independent from y, then you can replace this multivariate distribution with f of xx times f of y, and then separate the integral. Integral for dx, integral for dy, which is separate. I left this part for you. Mr. Mir Ahmadi or Mrs. Rajabzadeh, I will write this and will leave you with God. Covariance function, correlation function. Correlation function. We will denote correlation function by this in statistics, and then the argument for this is going to be x comma y, and then it's going to be defined as covariance of x and y divided by variance of x and variance of y. Standard deviation of x, standard deviation of y. Please pay attention that the unit for covariance is the unit of x and y times each other, but when it comes to the unit of correlation function, it is unitless. Because if you divide this by this, you will eliminate the unit. The unit for this is going to be unit of x times unit of y, and then this is the unit of x, and this is the unit of y, and that will cancel out. It will leave the covariant correlation function to be unitless. And this correlation function is between -1 and +1. از حوصله همگی سپاسگزار هستم. همگی رو خدا